over and over again, and it is really the driving force of our game. Godot of course does this automatically, but we can add functionality to the game loop using the other function in the template, process. Unlike ready, which only runs once, process runs every frame. This makes it perfect for doing things over time, such as moving an enemy. We simply make sure to change the position of the enemy a tiny bit each frame. So in our script, we can simply remove the pass keyword and instead access the position of our slime, more specific the x-coordinate of our position, and add 1 pixel to this every frame. Then in our game, let's go ahead and place a slime close to our player so that we can see this happening, and play. And as you can see, the enemy just shoots past us on the screen. Now one problem with this that might not be obvious other than it's moving way too quickly is that we are increasing the x position every frame by a fixed amount. And because our frame rate can vary, this means that the enemy will sometimes move faster than others, which is not very good. To fix this, we use this little thing here called delta. Delta is the amount of time that has gone by since the last frame. If we are drawing many frames per second, delta gets really small. And if we lag out a bit and are not drawing as many frames, delta becomes bigger. Because of this, we can use delta to compensate for variations in frame rate. If we have a high frame rate, we want to only move our enemy a little each frame. And if we have a low frame rate, we want to move it a lot. In other words, we can multiply our movement by delta to make it independent of the frame rate. Now, delta can be a bit hard to wrap your head around at first, but don't worry, you'll get the hang of it. A good rule of thumb is that whenever we have a speed value that we can adjust, such as our 1 here, we should probably multiply it with delta. So in our script, we simply go plus equals 1 multiplied with delta. Now what this essentially means is that we are going to be moving 1 pixel per second, which is not very fast. So let's instead change this to something like 60. And we can actually store this speed in a constant at the top of our script, just like in the movement script. So here I'll write const speed and set it equal to 60. Then we can simply use speed here instead of hard coding the value. This makes it easy to change constants right at the top of your script. And now if we play, we can see that our enemy is moving at a reasonable rate, and we know that this speed won't change from system to system. So let's get rid of this extra slime here, and instead make this one actually change direction whenever we face a wall. To do this, we need a way to control the direction we're currently moving in. So let's create a variable that does this. We'll create a var, call it direction, and set it equal to 1 by default. Then if we need to go in the opposite direction, we'll set it to -1 instead. And to actually apply this, all we need to do is multiply it into our speed. So we'll go direction times speed times delta. This is a really standard way of doing movement. We simply add onto our position in a direction, multiplied by speed and delta. So now all we need to do is check if the enemy gets close to a wall. And for this, we'll use a new type of node, the raycast node. Raycasts are invisible rays that we can shoot out to detect collisions. So inside of our slime here, let's add a new node of type raycast2d. And as you can see, it draws an arrow to represent this. Let's move the starting point here to the center of our enemy. And let's have it shoot out to around here. I'm going to rename this to raycast right. I'm then going to press Ctrl D to duplicate. I'm going to have this shoot out in the opposite direction and rename this to raycast left. Now in our script, we can reference these nodes just like we did with our timer. We simply select them both, click and drag, and hold down Ctrl while releasing. As you can see, this creates two variables, one raycast right and a raycast left. Then every frame before we move our slime, we will go ahead and check if we are currently colliding to the right or to the left. If raycast right dot is colliding, if this raycast is hitting something, well then colon, and then make sure to indent here with the tab. We will set our direction to be -1. If we are colliding on the right, we want to move to the left. And we'll add another one of these if statements. So if raycast, you guessed it, left dot is colliding, well then we'll set our direction back to 1. And that's it. Our enemy is now ping-ponging back and forth between the two walls. And this is happening completely automatically through script. Really cool. Now the only thing that is left is to flip the enemy sprite when it changes direction. Luckily, if we go inspect our animated sprite here, under offset, we have this flip age property, which will simply flip the sprite. So let's control this through our script. In our script, we'll get a reference to our animated sprite 2D. This creates a variable called animated sprite 2D. I'm just going to get rid of the 2D here to make the name a bit shorter. And then whenever we are colliding on the right here and we change direction to move towards the left, we will also go to our animated sprite and set the flip. In our left is to flip the enemy. Well, then we'll set the tab. We will set direction and rename this to route represent this. Let's move the starting point here to the center of our enemy, and let's set an invisible rays that we can shoot out to detect collisions. So inside of our slime here, let's add a new node of type raycast2d, and as you can see, it draws an arrow to represent this. Let's move the starting point here to the center of our enemy, and let's have it shoot out to around here. I'm gonna rename this to raycast right. I'm then going to press Ctrl D to duplicate. I'm going to have this shoot out in the opposite direction and rename this to raycast left. Now in our script, we can reference these nodes just like we did with our timer. We simply select them both, click and drag, and hold down Ctrl while releasing. As you can see, this creates two variables, one raycast right and a raycast left. Then every frame before we move our slime, we will go ahead and check if we're currently colliding to the right or to the left. If raycast right dot is colliding, if this raycast is hitting something, well then colon, and then make sure to indent here with the tab. Now in our script, we can reference these nodes just like we did with our timer. We simply select them both, click and drag, and hold down Ctrl while releasing. As you can see, this creates two variables, one raycast right and a raycast left. Then every frame before we move our slime, we will go ahead and check if we are currently colliding to the right or to the left. If raycast right dot is colliding, if this raycast is hitting something, well then colon, and then make sure to indent here with the tab. We will set our direction to be -1. If we are colliding on the right, we want to move to the left. And we'll add another one of these if statements. So if raycast, you guessed it, left dot is colliding, well then we'll set our direction back to 1. And that's it. Our enemy is now ping-ponging back and forth between the two walls. And this is happening completely automatically through script. Really cool. Now the only thing that is left is to flip the enemy sprite when it changes direction. Luckily, if we go inspect our animation, just such as our 1 here, we should probably multiply it with delta. So in our script, we simply go plus equals 1 multiplied with delta. Now what this essentially means is that we are going to be moving 1 pixel per second, which is not very fast. So let's instead change this to something like 60. And we can actually store this speed in a constant at the top of our script, just like in the movement script. So here I'll write const speed and set it equal to 60. Then we can simply use speed here instead of hard coding the value. This makes it easy to change constants right at the top of your script. And now if we play, we can see that our enemy is moving at a reasonable rate, and we know that this speed won't change from system to system. So let's get rid of this extra slime here, and instead make this one actually change direction whenever we face a wall. To do this, we need a way to control the direction we're currently moving in. So let's create a variable that does this. We'll create a var, call it direction, and set it equal to 1 by default. Then if we need to go in the opposite direction, we'll set it to -1 instead. And to actually apply this, all we need to do is multiply it into our speed. So we'll go direction times speed times delta. This is a really standard way of doing it. This creates a variable called animated sprite 2D. I'm just going to get rid of the 2D here to make the name a bit shorter. And what is left is to flip the enemy sprite when it changes direction. Luckily, if we go inspect our animated sprite here, under offset, we have this flip age property, which will simply flip the sprite. So let's control this through our script. In our script, we'll get a reference to our animated sprite 2D. This creates a variable called animated sprite 2D. I'm just going to get rid of the 2D here to make the name a bit shorter. And then whenever we are colliding on the right here and we change direction to move towards the left, we will also go to our animated sprite and set the flip age property to true. And when we are colliding on the left and we're changing direction again, well, then we'll go to our animated sprite and set flip age back to false. And that's it. That's our entire script. Let's find our enemy here and hooray! We've made an enemy, and a slimy one at that. But of course, dying to the enemy could definitely look cooler. So let's fix that. Dying 2.0. Let's start by adding a slow motion effect when we die. We can do this by changing the time scale of the entire game. So inside of our kill zone, we'll open up the script here. And right after we print you died, let's modify our time scale. So I'll go engine.timescale and set it equal to 0.5. This means that we will go at half speed. Then when our timer runs out, let's set this back to default, because otherwise we will actually still be slowed down when our scene reloads. So we'll go engine.timescale and set it back to the default 1. And if we play this now, this is actually already much better. Notice that it also takes twice as long before the game restarts, because everything in our game slows down, including our timer. But I think it could be even cooler if we remove the player's collider to make him simply fall off the map. To do this, we need a reference to the player. We actually already have this here. You'll notice that after the onBodyEntered here, there's a variable called body. This refers to the body that entered the area. And since the only thing that enters the kill zone is our player, body is our player. So we can actually add a new line here that goes to our body, and then we simply need to get the collision shape node under our player. So we'll do dot get node, and we'll search for the collision shape 2D, and we can remove it. So call dot queue_free on that node. Again, queue_free means to remove that node. So here we're accessing our player, getting the collision shape node, and removing it. And now if we find our way to some danger, boom, we are hit and we fall off the map. Cue the sound effect. Whoa! Player 2.0. So far, we've been using the character movement template pretty much as is, but we need to modify it in order to add animation to our player, as well as change the key bindings that we use to move. So what are we looking at here? Well, the top two lines define two constants with our speed and jump velocity. There's also a variable here that defines the gravity based on our project settings. By default, this is a value of 980. So we have these three values, but the meat of the script is really inside of this physics process function. Physics process is very similar to the process function we used for our enemy. However, while process is great for a lot of things, there is one part of the game engine that really struggles with not knowing how many times per second it is going to be run. Run process looking at cue the sound finder, getting the collision shape node and removing it. And now if we find our way to some danger, boom, we are hit and we fall off the map. Cue the sound effect. Wah! Player 2.0. So far, we've been using the character movement template pretty much as is, but we need to modify it in order to add animation to our player, as well as change the key bindings that we use to move. So what are we looking at here? Well, the top two lines define two constants with our speed and jump velocity. There's also a variable here that defines the gravity based on our project settings. By default, this is a value of 980. So we have these three values, but the meat of the script is really inside of this physics process function. Physics process is very similar to the process function we used for our enemy. However, while process is great for a lot of things, there is one part of the game engine that really struggles with not knowing how many times per second it is going to be run. That is the physics engine. Physics in general need to update at fixed intervals to avoid janky behavior. Luckily, physics process solves this problem because it runs at a fixed rate, 60 times per second by default. This is independent of your game's actual frame rate and helps physics run smoothly. We use it for anything that involves the physics engine, like moving something that should collide with its environment, such as a player character. So in this function, a few things are happening. If the player is not standing on a surface, we add gravity. If we press the spacebar and the player is on a surface, we jump, and then we get the direction we need to move in based on what arrow keys are pressed and move accordingly. Now let's start by rebinding some input keys. For this, Godot uses an action system. We create actions for anything we want to do in the game. Jump is an action, so is move left or move right. We can then bind keys to these actions. Let's try it out. So let's go to Project, Project Settings, Input Map. And here we can add some actions. I'm going to add a jump action, as well as a move left and a move right. Then we can use the plus sign over here to bind a key. So to my jump here, I'm going to hit plus, and then it's listening for input. So I'm going to press the space bar and hit OK. And as you can see, space is now bound to jump. For a move left, I'm going to bind the left arrow key, and I'm also going to bind the A key. So we can use vast for movement as well. As you can see, there's no problem binding multiple keys to the same action, which is really handy. I'm also going to bind right arrow to move right, as well as the D key. And now we can use these actions in our script. By default, Godot uses some built-in actions that are meant for navigating UI. This is why it says things like UI accept here. Let's replace these with our own actions instead. And as you can see, it will actually help us by auto-completing here. So I'm going to put in jump for my jump action. And then for moving left here, I'm going to change to move left. And for moving right, I'm going to change to move right. And now we can use the keys bound to our actions to move around, which in my case are both the vast keys and the arrow keys. Awesome. The next thing we need to do is to update our player graphics to face the direction we are moving in, and to play the right animation. Let's start by flipping our sprite based on direction. So just like with our enemy, we first need a reference to the animated sprite node. Again, here Here we can simply click and drag and hold down Control. Again, I'm going to remove the 2D from the name to make it shorter, and then we'll add some extra code to our function. Now, this line here defines a variable called direction that is based on our input. If we don't press any buttons, direction will be 0. If we press move right, direction will be 1. And if we press move left, direction becomes -1. So we can use this variable to check if we are moving left or right. I'm going to make some space in the code here and make my own comments as well. So use a hashtag for a comment. This here gets the input direction, which can either be -1, 0, or 1. And this down here actually applies the movement. So in between, we can add a section that flips the sprite. To do this, we check if our direction variable is greater than 0. Well, that means we are moving to the right. And we can set animated sprite dot flip horizontally to false. If this is not the case, well, then we want to check if our direction is less than 0. For this, we can use the else if or elif keyword. So else if our direction is less than 0, well, then we'll set animated sprite dot flip age to true. And now if we play this, we can see that our player sprite indeed faces the right direction. Now let's add some animation. So let's go to 2D view, select our animated sprite, and let's add 2 new animations. One called run and one for jumping. In our run animation, I'll add some new sprite frames. Select our knight. Remember, this is 8x8, and I'll simply add all of the frames in the run animation, which stretches over 2 lines here. I'll add those frames, set the FPS to 10, and play. Looks good. Then for the jump animation, I'll also add a sprite frame. And there are a bunch of different ways to go about this. But in our case here, I think we should actually play our jump animation whenever we're just in the air. This means that this will also play when we're just falling off a platform. And for this, we could use a very quick looping animation or simply a single frame. I actually like this one from the roll animation, so I'm just going to use that. Then in our script, we can of course play these animations. So after we get the input direction and flip the sprite, let's add a new segment, which is going to play animations. And here we also need to check our direction variable. More specifically, if our direction is equal to 0, well then we're standing still. And we can go ahead and play animated sprite dot play the animation called idle. If this is not the case, so else, well then we want to play animated sprite dot play the run animation. And that's actually it. If we now start running, we can see our run animation being played. Finally, we just need to add our jump animation. And here we can use a built-in function of our character body 2D, which is to check if we are standing on the floor. So at the top here, we'll check if we're currently on the floor is on floor. Well, then we want to go ahead and play our idle or run. So I'll cut this using Control X, paste it in here, make sure you tab in. And if we are not standing on the floor, well, then we're in the air and we can go and play animated sprite.play our jump animation instead. So if we're on the floor and our direction is 0, well, then we're playing idle. If it's not 0, well, then we're playing run. And if we're not on the floor, we aren't doing any of those things. We're just playing the jump animation. And that's it. Now if we play, we have a fully animated knight. I like to think that she's a former princess who got so tired of waiting to be saved from the big bad dragon that she took matters into her own hands. Who better to save some princesses from a dragon than someone who knows dragons like her own back pocket? But feel free to make up your own story. And that reminds me, story. We need a good way of communicating story, hints, and other valuable information to the player. And to do this, we need text. So let's add some text elements to our game. Text. There are multiple ways of working with text in Godot, as part of a larger UI or as an integrated part of the game world. For this game, I decided to try making the text part of our world. In Godot, a text node is called a label. So let's add one. Let's hit Ctrl A and search for a label. Let's focus on it. And as you can see, this creates kind of a bounding box for our text. So I'm going to put it over here and scale it up a bit. And let's add some text in the field here. I'm going to put in a gameplay hint. And as you can see, the text looks really blurry. That's because since we're using pixel art, we're actually zoomed in really, really far, which makes the otherwise smooth text appear blurry. So we can fix this by using a pixelated font with hard edges to match our style. I've of course included some in the assets. So let's go under theme overrides on our label, fonts, and here we can drag in the pixel operator font. We can also change the font size under font sizes here, enable that, and I'm going to set mine to 8. Note that we have to use multiples of 8 in order for the text to appear crisp. So you can see if I change this to 9, it becomes blurry again. But we can use 16, 24, 32, and so on. I'm also going to go to the colors here and change the font color using the color picker. And now we can place these text elements around our game to provide story or gameplay tips. Once we're happy, we can categorize all of them under a node. So let's create a node, call it labels, and drag all of them under that. And now when we play, as you can see, they appear as a natural part of our game world. And just like with sprites, because the player character has a greater Z index, it will draw on top. So let's use one of these text elements to display our current score. Score and points. To create a score or coin counter for our game, we need two things: a script that keeps track of our current score and a label to display it. It's common practice to place game-wide variables such as a score inside some kind of game. Score and points. To create a score or coin counter for our game, we need two things: a script that keeps track of our current score and a label to display it. It's common practice to place game-wide variables such as a score inside some kind of game manager. So let's make one. We'll hit Ctrl A to add a new node. Let's rename it Game Manager, and I'll place it right at the top here. The reason why we are using a regular node and not a node 2D is because we don't need our game manager to have a transform, in other words, a position, rotation, and scale. Now let's add a script to our game manager. We'll use the empty template, and for the path here, let's put it inside of our scripts folder, and let's also rename it with non-capital letters. Create, and let's create a variable for our current score. So we'll write var for variable, name it score, and default it to 0. Now, so far in our code, we've only used the built-in functions of Godot, and some that we made with signals. In this case here, we want to create our own function that adds adds a point to our score and displays it. So I'll write func for a function. We'll name it add point, open and close some parentheses, and put a colon. Then on a new line, we'll write score plus equals 1 to increase our score by 1, and print our current score. Now, unlike ready, which runs at the start of our game, and our signal functions, which run when a signal gets triggered, this function currently has nothing that calls it. So right now our function is here, but it isn't being run. To change this, we need to go into our coin script and tell it to call this function whenever a coin is picked up. So inside of our coin script, we need a reference to our game manager. But if we just click and drag while holding down Control, we get this really weird looking path. This is because the game manager is higher up in the tree than the coins. And it's generally bad practice to use paths like this that try to access nodes at the same level or higher in the tree. Luckily, because our game manager is a one-of-a-kind and we are sure that there will always be only one game manager, we can solve this by marking it as unique. So let's right-click our game manager and select Access as Unique Name. As you can see, this creates a percentage icon next to the game manager, letting us know that it's a unique node. This makes it much easier and safer to get a reference to the game manager, because now when we drag it in, instead of a $sign with a weird and unpredictable path, we get a percentage sign, which means that Godot quickly finds the node via its unique name instead of using a path. One limitation of this is that you can only access unique nodes from within the same scene. If the game manager and the coins were in different scenes, this wouldn't work. Now in our function, we can replace the print line here with game manager, access our game manager, and call the function add point. And now when a body enters our coin, it's going to go to the game manager and run our add point function. And if we play, we can see that every time we pick up a coin, it increases and prints our score in the output window. Finally, we can use what we learned about labels in the previous chapter to create one for displaying our coins. I'm going to make a little place for this in our level. For now, I'll just put in some text that says you collected X amount of coins. I'm also going to change the auto wrap mode to word. Now we can wrap our text and the horizontal alignment to center. Finally, I'll use a bolder font. Now we can take this label and rename it to something like score label. And since we want to change it from our game manager, let's drag it right under our game manager. Now in our script, we get a reference by clicking and dragging, holding down Control. And instead of printing our score, we'll go into our score label and access the text property and change it to you collected. And then here I'm going to add the number, add the score onto that amount of coins. Notice how I make sure to add spaces between the words. And while this looks good, it's actually going to give us an error. And that's because we need to change this score here from a whole number variable called an integer into a text variable called a string. Again, we'll talk much more about variables in our video on GDScript. But for now, we can cast this using str for string and then wrapping it in parentheses. And now when we play and pick up some coins along the way here, once we get to the end, it says, great job, you collected 6 coins. And if I pick up another one, it's going to update to 7. Awesome. And I don't know about you, this is great and all, but I think it's distinctly lacking a bling sound when we pick up a coin. Bling, bling, bling. Bling. Audio. One of the things that often get overlooked when making a game is audio. But music and sound effects are a huge part of building the mood of your game. This is of course a beginner's tutorial, but let's at least get our feet wet, or should I say our ears wet? Nope, I shouldn't. Let's at least add a music track and a pickup sound for our coins. Now in the assets, I've included a music track as well as a few sounds. And to play these, we need a new type of node, the audio stream player. So let's add a new node, search for audio stream player 2D. Let's rename this to music. Then we can take our music track here, Time for Adventure, and drag it into the stream slot. We're also going to set it to autoplay. And by default, this is not going to loop. To change that, let's double click it. This is going to open up our audio importer. Here we can preview our music track. Groovy. Anyways, we can loop. So let's enable loop here and hit re-import. Now by default, all sounds are played fairly loud, and since this is background music, we probably want to turn it down a bit. We can do this by adjusting the volume on each individual AudioStream player, or we can use the audio tab here at the bottom. This is actually a fully functioning audio mixer, and we can add different buses to control our audio. Let's add two, one for our music, as well as one for sound effects. And then we can simply route our music here into our music bus. So now we can control the volume of our music using this slider. I'm just going to set it to -12. And we have music. Unfortunately, it's going to restart whenever our scene is reloaded. A quick fix for this is to take our music node and make it into a scene. So I'll click and drag it into our scenes folder, hit save, and then we can add this scene as an auto load. Autoloads are global scenes and scripts that we want to persist throughout our entire game, no matter which scene is currently loaded. So let's remove music here from our game scene and instead go to Project, Project Settings, Auto Load. We'll click the little folder here and navigate to our music scene and hit Add. We've now registered our music scene as an auto load, which means that if we now play, even though our music scene isn't in our game, it automatically loads and starts playing our track. And even better, it doesn't reset when our game restarts. Now to add a pickup sound, we go to our coin and add an audio stream player. Let's rename this to pick up sound, drag in our coin sound, and set the bus here to sound effects. And now we can actually play this sound through script. But since we are removing the coin immediately by calling the cue-free function, the sound won't actually get a chance to play. We can of course fix this by adding code that waits until the sound has finished playing, but then we might get weird functionality where we try to pick up the coin multiple times while it's playing, and it will still be visible until the sound is finished. So let me show you a really cool trick to get around tricky timing things like this without writing any code. That is using an animation player. So let's add an animation player. And here we'll create a new pickup animation. And the first thing that we want to do when we pick up the coin is to hide the coin sprite. So I'll go into the animated sprite 2D, and this will change the window. So I'll go back to animation here. And now under visibility, I get to keyframe the visible property. Now when working with animations that don't need to play until later in the game, it's nice to be able to go back to the default values after animating. By default here, our coin should be visible. Now, this is pretty cool. If I just create a keyframe here for the default value, Godot is going to ask to create a reset track. If we say yes to this, Godot is automatically going to create another animation track called reset that will simply reset this value to its default state. So now in our pickup animation, we can keyframe it to whatever we want. In our case, when we pick up the coin, we want it not to be visible, so I'll disable that, keyframe it. And then if we want to go back to our default values, we simply go to our reset track and there it is. It goes back to default. So let's go to our pickup. Let's also modify our collision shape. We don't want to be able to collide with it while it's playing the sound. So let's simply go ahead and add a default key here for the disabled property. Hit create. And now we can set disable to true and add a new key. We can also go into our pickup sound here. And let's add a default key for the playing property. Let's hit create. And now since the sound plays pretty quickly, I can actually reach the key in time. So we can go down here instead. I'm just going to scale this up a bit. Go down here to the value, the keyframe here, and change it to on. So we can actually modify the keyframes here as well. So now we have our pickup animation. And if we go to reset, we can see that everything goes back to default. So that's just a nice way of working with animation. So now we play the sound, disable the collider, and hide the sprite. After 1 second though, we can go ahead and remove the coin from our scene. So all of these keyframes here are on second 1. Let's put them over to right at the beginning of our animation at second 0. And then after 1 second here, we want to remove our coin. And this is a really cool part about the animation system, is that we can actually add another track here, a call method track, that is used to calling functions. So on our coin, we want to call a function, and I'll right click right where we want to do that, insert key, And the function that we want to call is the queue_free method, which is right here. And so now, after 1 second, it's going to call the queue_free method on our coin without us writing any code. And voila, all the things we could have done through code are all inside this animation. And again, to get back, we simply choose reset. Now all that is left is playing the animation through script. So in our script, we'll get a reference to our animation player. And then instead of directly calling queue_free, we'll go animation player.play pickup. And if we play now, we can hear our music and we can hear our pickup sound when we run into the coins. Awesome. Export! Finally, we are ready to export. Really incredible that you made it this far. You can feel very proud. So let's get our game out of Godot so we can share it with others. Godot can of course export to many different platforms, but I'm on a Windows computer here, so let's go ahead and make a quick Windows build. The first time we are exporting our game, we need to download the export templates. These are a little large, so to keep Godot lightweight, they aren't included by default. To install them, we go to Editor, Manage Export Templates, and hit Download and Install. And the export templates are installed and ready to be used, so we'll close, go to Project, and Export. In this window, we'll add a build platform, so let's go Add, Windows Desktop. We'll enable Embed PCK, which will export it into a single file. Then we scroll down. As for the product name here, I'm going to type in Princess Dragon Slayer. And we can hit Export Project. I'm simply going to put this on my desktop, uncheck Export with Debug, and hit Save. This warning is not a problem, we'll hit OK. And now on the desktop, we have this first game.exe. We can open that up. And voila! We made a game! Woohoo! And that's it! Congratulations on making your first game in Godot. If you don't understand everything or are unsure about where to go from here, don't worry. That's totally normal. It takes a little while to become familiar enough with the tools to feel really free with them. Never hesitate to use the documentation, tutorials, or code examples you find online. When I started out, I spent a lot of time remixing other people's scripts before I started to write my own. Now, where